Hello. Good morning.
Good morning.
How is everyone this morning? Was the test we had, is the test we had on Monday the only test this week, or what else is going on?
It's the only one for me.
Okay. So how many tests you actually just don't have, or did any of them get sort of canceled because of the situation, or like some of these like second midterms?
I'm in a gov class and they just did like a weekly quiz and it adds up to the same percentages the midterm.
Was the overall experience on Monday okay? I didn't get to grade yet and read through the comments that you might have left.
I was a bit confused on the part A of number 1, the like Kármán permeability with the
Kármán-Kozeny equation?
Yes. Just
What?
how we were supposed to decide what the tortuosity was.
Well, the cubic packing is kind of straight, so it's 1. It's not tortuous.
Okay.
That was by looking at the picture. So, but that said, in reality, that tortuosity factor is kind of like a factor you have in there to account for everything that you're actually missing with that equation. So it often ends up being a fitting parameter so that you can actually fit the experimental data. In that picture, I just expected you to make an assumption based on what you see. And part of that sort of like problem is that, okay, if you have Kármán-Kozeny equation that was developed for slightly similar but not the same problem, and if you have the bundle of tubes model, they're gonna, where you approximate the cross section with some approximate shape that you know the result for, you're gonna get 2 different estimates, and that's somewhat of a reality in porous media because all of these equations are essentially correlations and simplifications. So all of them are missing something. Does that make sense?
Yes, thank you.
Yeah. Okay. Well, I think I'm gonna get going with the, that's not it. Just a second, I have wrong presentation open. All right, this is the one. Share screen. All right. So we're going back to MassTransport as I can have my pen to write. So essentially, what we had is tracking individual species within a mixture. And in this case, we're looking at, again, molecular species, and we're looking at their concentrations. So the essence of anything, I guess, in transport is that if I have a gradient in concentration or a gradient in temperature, gradient in pressures or velocities, then some motion or transport will happen to equilibrate those. So in this particular case, we're looking at the gradients of concentrations. So I'd like to actually first, in writing, kind of, instead of flashing you with the PowerPoint all of the time, let's review the terminology a little bit in writing. And then we're going to get to solving a problem today. Review the equations and solving the problem. So essentially, we have Oh, okay. Row A, what did I refer to as row A? Mass concentration. And that's equal to mass of species A divided by V. Okay. And then basically, if I have, let's say that I have a binary mixture, then row A plus row B gives me overall density or mass density, right? Now, if I actually divide that row A by row, I will get omega A. So that's just mass fraction. And all of my omegas, however many I might have, will add up to 1. So if I have more than 2 species, I'm going to have the sum of omegas equal to 1. Then we're going to get the basically similar thing, but we can also track molar concentrations. Okay, and that's going to be number of moles of A divided by V. And then by the same, it's sort of like equivalent thing. I'm going to have XA, which is my CA divided by overall number of moles C. So that's molar fraction. So I can track individual contributions of everything. So basically, I can also split my velocity. I can have VA. Now, let me change color for this. Just a moment. So I can also have VA as a velocity average for species A only, and it's with respect with respect to the center of mass. So velocity of species A, and my V, my overall velocity, is basically a fraction of a VA. Sorry, my fat fingers are at work. All right, omega A VA plus omega B VB. And then again, I have equivalence for molar, which can be slightly off. Mass and molar splitting velocity is for mass and moles, it can be slightly different. Okay. So then my V star is XAVA plus XBVB. Okay. And here I can see if I multiply by rho V, which is my momentum, I'm going to have rho A VA plus rho B VB. Okay, now what is our equivalent of Newton's law or Fourier's law? It is called Fick's law. And that equivalent says that mass flux of A, if I have a gradient in concentration, and if I have a gradient in concentration, I'm going to have a gradient in mass fraction as well. So it's expressed using mass fraction. It's equal to minus, we're already used to these things that are negative times the transport coefficient times the gradient, right? And now I'm going to express it with gradient of omega A. Since omega A doesn't have units, then units are there of rho. And then DAB is my diffusivity of A within B. DBA and DAB are the same thing, so technically I could have called it D, but the book refers to it as DAB, so I'm keeping up with it. Okay. So that is my flux or mass flux of species A just with respect to the gradient in mass concentration, and if there was absence of anything else, such as actual convective motion of the fluid overall, okay? And if I account for that, then I'm going to have combined flux mass flux, and that's equal to this JA and plus whatever might be carried into my volume. And then I have the equivalents for this, which are basically molar combined flux, and that one we refer to as uppercase N, and that's molar equivalent. I can go back and forth these two, and I can remind myself that rho alpha is C alpha times, or let's speak in terms of A, sorry, is CA MA. So Ca is my molar concentration, and this is my mass or molar mass. This is from chemistry of component A. And this, of course, the equivalent of this is true for B or for any other, however I wanted to call these, however I wanted to call the components. If I have more than two, then I kind of tend to refer to them as alpha, and alpha is 1, 2, 3, 4, and so forth. Okay. And then finally, to do any balance, we were doing this balance last time. Again, just like in any shell balance, I was actually deriving a general equation that actually had a time component to it, but those we derive using a shell balance as well. It's just that we're going to possibly have an accumulation term. So basically, when I'm looking at a shell, in this case in Cartesian coordinate system, then I look at the combined flux and what is coming in and out of the boundaries. And I collect all of those terms. And basically the operation that, or differential operator that collects all of those terms over different boundaries is divergence. So you will get that derivative of rho alpha rho t is gradient of n alpha plus r alpha. R alpha is a rate of production, which is basically how much per volume do I produce of my species, alpha in this case. And if I had two species, then typically rate of production of one plus rate of production of the other is 0, because we have mass conservation. I cannot just produce something from nothing. Okay. And basically, we got overall when we did that balance that this is true, but when I sum it up, I actually get my equation of continuity, which is conservation of mass. So this was my basically sum of all terms. So the procedure in solving for problems is pretty much similar to what you would expect at this point from any shell balance. So now if I had basically my previously, so there was this conversion, right? So if I had my what is essentially equation of continuity for individual species. So this is my D rho. Let me change color a little. How about I go back to black? So this was my expression for any species alpha. So alpha could be A, B if I had my binary mixture, or I could have a number of them. So if I wanted to sort of translate that in molar equivalent, I would use this part. So essentially, if I have, so my R alpha, I did not have this on the list, so let's add it. R alpha rate, or I'm going to call it RA since everything is in terms of rate of production of A per volume. And then the similar thing is, this is mass rate. And uppercase R will be my molar rate of production, or it might be consumption, of course, when I say production. So if I wanted to translate this, I would just basically, if I multiply or divide this by MA, so these two things would give me that, for instance, this CA dt is divergence of N alpha plus R alpha, right? So one can go back and forth in expressions using moles or mass. So let's actually try to do one of these shell balances. So just like I derived the equation of change using shell balance, I'm going to use it now in a problem. My problem is actually borrowed myself a book, a picture from the book, but you can draw it yourself. So this is going to be an example. This example is in BSL chapter 18.2. And it's dealing with a diffusion Okay, I'm gonna turn off my virtual background because it's doing some strange things. Choose. No, turn off. None. There we go. So you're gonna look at my ceiling. But better than those strange changes because it cannot, I think it's looking for faces and my face is only in part when I'm writing. So that's not working out well. All right, so this is diffusion through a stagnant film. So here's what's happening. I'm going to assume I have a beaker and I have a liquid A at the bottom. Vapor of A, and then above that, I have gas that I'm referring to as B. So at the interface of A and B here, at that interface, vapor of A, so I'm going to say vapor of A, is diffusing through B. Okay. And then here, let me change color a little bit. Oh, never mind. So here I have gas B. Okay. So my vapor of A is moving up and then up at where Z is equal to Z2. So this is my coordinate system has really just one direction, Z. Here, upwards at Z is equal to Z2, I have some sort of a gas stream, a fan, that is removing both A and B. So it's basically maintaining a steady concentration of A. And now, because I have what you could call super concentration at the interface of liquid A, I have basically the concentration that corresponds to the equilibrium of these two interface of the liquid and A. So that's gonna vapor of A. So that's gonna give me sort of the maximum I could have for concentration of A here at the bottom. And then at the top, since I keep removing both, I have some other concentration that is kept constant. Maybe it's 0, maybe it's some constant, but I know what it is, right? So I can say, XA here is some, I'm going to call it XA1. And XA here is some sort of XA2. Okay. So those are known concentration. Here we go, my fat fingers at work again. Known and known. Okay. And I will assume that A and B sort of like ideal gases, and my concentrations overall are not very high, so I can do certain simplifications. Okay. So now I'm wondering, okay, within this beaker, what is my, I know that my XA is somewhere between XA and 1 and XA2, but what is it, right? So let's do balance. Now, this problem is I don't have any changes of A and B, like beaker is closed. So this is going to be, by nature of that, a one-dimensional problem. The only thing that can change something, I expect across all of these cross sections to have similar situation. So the only direction that is of importance is, so basically I will have 1D problem in the direction, just as shown in this plot. And now if I assume that there is some cross-sectional area S, okay, then what do I know? I have a shell already drawn here. Oops. One of these days, I'm gonna learn which little. So here's my shell. And it has thickness delta Z. So what does my mass balance for? This is stated in terms of molar concentrations, okay? Or more molar fraction. So this is molar fraction. So I'm gonna also use molar flux, combined flux. So if this is flux Na, so Na is my combined molar flux. What has to be true? How do I get everything that comes in through this boundary right here? I have Z and I have Z plus delta Z. Anyone? Is what comes in Na, or do I have to modify it somehow to get the total amount? Anybody awake? I'm waking up slowly this morning.
Do you have to add the rate of production?
I don't have production, but I have to, what do I, it's Na is a rate, but it's divided by area, right? So what do I have to do?
Multiply by area.
Multiply by area. And this time I'm, for obvious reasons, not calling area A because A denotes my species A, right? So I'm calling it S, yeah? And that area is same here and same here, so that's nice, that's simple, okay? So S, and then on the other side, nothing goes through the other boundaries. This is why it's one-dimensional problem. And on the other side, I'm gonna have Na is Z plus delta Z. And now if I had production, I would add it here, but I have 0 plus 0 rate of production. And I'm looking at this in steady state. So when I sum all of these up, I had to get a 0. So there's no accumulation for steady state. Yes? So I can, of course, now divide by S. I can also divide by delta Z, or the, well, I can divide by the volume of this, which is S times delta Z. So divide by shell volume, which is S delta Z. And I'm going to get that negative A Z plus delta Z. So this is basically negative NA at Z plus delta Z minus NA at Z divided by delta Z is equal to 0. Does this look familiar at this point? I take a limit as delta Z goes to 0, and I will get a derivative in Z direction. So this is equivalent to what we had for energy. We had D, EZ or EX, I'm forgetting which, whether we used Z or X direction last time around. So a lot of times I will get this form, and it's somewhat deceptively simple because I didn't plug in what NA is. And NA is my combined flux. So whenever I have combined flux, I have sort of like my basic law, in this case, Fick's law, plus addition of stuff that just like moves into my volume. And we had lowercase na, which was for mass, but this is for molar part. So for molar equivalence, I have molar equivalent of Fick's law. And this na will be simply the, I'm going to call it uppercase JA, and book likes using star for molar. So this is just equivalent of JA for molar, and plus CAV star is basically the convective part. So concentration of A carried in with my molar average velocity V star. So this by definition is minus, instead of rho, I simply just have C DAB. And instead of gradient in omega, I have gradient of XA. This is just my molar equivalence. So let me just write it down so you have visually. So I have essentially JA is minus CDAB gradient of XA, whereas my lowercase, the mass version of it, was minus rho DAB gradient of omega. Okay? That's just Fick's law. Okay, and then plus, I'm sorry, I stopped in the middle. So this is the Fick's law, and the convective component is XA CV star. Now CV star, by definition, it's basically molar version of my momentum. I'm gonna keep writing this. or just rewrite this part, plus XA is, by definition, it's CA VA plus CB VB, which is essentially my NA plus NB by definition. So just add all of the species really in their molar fluxes. Cool. Now here is the basic problem of when I'm working with diffusion problems. Okay? I'm gonna rewrite this part because it's important and we're gonna use it a lot. My NA is XA plus XA NA plus NB. Okay. This is the general equation. And the basic problem is that when I'm solving for concentration of species A, I have B coupled in. Well, and that bothers me, right? Because then I have to also solve for B. So most of these problems in diffusion, I have to, based on what is happening, figure out how to express NB in terms of NA. Okay? So that's the essence of this problem. And also, I'm never really solving for NA. I'm solving for things that I can measure, like concentrations. Just like in energy problems or energy transport, we never solve for E, we solve for temperature, which we can measure. Okay? So key issue, express NB in terms of NA, or rather that's equivalent of saying XB in terms of XA, because I want to solve for XA. This is what I'm solving for. In this case, I have keyword will be, we had a diffusion through a stagnant film. So this was diffusion of, whoa, my fat fingers in, of A through a stagnant film of B, right? So stagnant film B, I will just assume that this flux of B, yes, it exists. That actually it's counter, even if I have flux of A and B is static from me watching from the side, technically relative to its center of mass, some of it is moving to counter a movement of A, but I'm gonna assume that overall the flux of B is not a big deal and it's relatively static. The stagnant film in this problem allows me to say, okay, NB is approximately 0. It's not 0, but it's close to 0. Okay. So then I have simplified, so I have NA here and I have NA on the other side. So basically 1 minus XA times NA is equal to minus CDAB gradient in XA. In this entire exercise, I did, so my NA is minus CDAB minus XA gradient in of XA. And I needed NAZ because I had a Z component only in this case. So my NAZ is minus CDAB over 1 minus XA X, A, Z. Dx, oh, gradient, look at me. Really? The component of the gradient is dx, dxa dz, right? So I'm just taking z component. Is everybody comfortable so far? So just like before, just a quick recap. We do a balance. We do a balance on my, in this case, molar flux, combined molar flux. So I get this equation that looks simple. Oh, derivative in z direction of this combined molar flux Na has to be 0. And then I have to basically unwrap what is this combined flux. That combined flux has the part of it that is Fick's law, and then the convective part that just kind of moves in. So Fick's law just happens just because of the gradients without anything else moving. And I also, so I separate that from actual convection of things being brought into the volume. So that is my combined flux. And when I write it down, I get that my combined flux of A depends both on combined flux of A and B. That bothers me. I gotta figure out how to express B in terms of A. And in this particular case, we have a stagnant flow. We're gonna have different situations as we go throughout. And specifically when we have reactions, we have to work differently. But in this particular case, this is fine. Okay, so that it allows me to then simplify this and express NAZ in terms of just XA. And the derivative of that, since D, NAZ, DZ, that's what I'm actually solving, is equal to 0. So if the derivative of this expression in terms of XA is 0, that means that minus C DAB over 1 minus XA times DXA DZ is equal to some constant. And I'm going to assume that, and this is an assumption again, that for the concentrations that I'm working with, molar concentrations, neither the diffusive constant nor the C are changing. So I'm going to assume, and for smaller concentrations, that is okay. C DAB is constant as well over the ranges that we are solving for this problem. So nothing is changing my diffusivity and so forth. So that basically means that I can divide, and of course I can divide by -1. So that means that 1 over 1 minus XA dXA dZ is some constant C, C1. I'm not going to call it C. C1 is better because C means something else in this context. So when I integrate, does anybody see how to integrate this? I'm going to let you take a look at it a little. Any ideas?
Bring the DZ on the other side, right?
Mm-hmm. Yes.
And then then you integrate, and then that should be, is that an R? No, is that 1 minus?
Don't let minus bother you. Minus is the simplest thing. Do you see a logarithm in there?
It's going to be ln of 1 minus xa.
Mm-hmm. And that
All right.
minus, we're just going to put in. So it's minus ln 1 minus xa. Does everybody see the chain rule? Is some C1z plus, that's when I integrate dz, right? Plus C2, some other constant. Okay, cool. Now what do I need to actually solve this? To find C1 and C2, I need
Boundary condition.
boundary conditions, of course, and boundary conditions make all of the difference. But here I'm saying, okay, xa is xa1, at z is equal to z1, and xa is xa2 is equal, z is equal to z2. So my BC's xa of z1 is xa1, and my xa of z2 is xa2. So then I can solve that. I can plug in both of those. Plugging both over there. So I can, these are two equations. If I, let's say 1 or 2, I can do 1 minus 2 to get rid of C2. And that gives me that C1 times Z1 minus Z2 is basically ln. So I also remember how I can manipulate logarithms. So that gives me C1. Everybody comfortable with this? And then my C2 is when I plug it in. So for instance, the second one or the first one, either way, I'm just going to write down what I get, Z1 over Z1 minus Z2, ln 1 minus XA2, 1 minus XA1, minus ln of 1 minus XA1. So my C1 and C2 look like a mess, even though it really looked simple at the beginning. Minus ln of 1 minus XA is C1Z plus C1 plus C2, and look at C1 and C2. But it can be worked out. So now I plug it in. Technically, the problem is solved. It just looks a little messy. Minus ln minus xa is C1 times Z. So that's Z over Z1 minus Z2. Plus Z1 and then when I bring this part on the other side, I'm going to have 1 minus XA1. So it was ln of that number minus ln of 1 minus XA, and I'm just gonna bring that into the same one. Is Z minus Z1, Z1 minus Z2, ln of 1 minus XA2, 1 minus XA1. And one final manipulation is that, well, this is some number that I can put as an exponent right here. Pepper, shush. That's my dog. When I teach, she's under my feet. So when I do that, then I can actually get rid of ln. So 1 minus XA1 over 1 minus XA is 1 minus XA2 over 1 minus XA1 to the exponent Z minus Z1, Z1 minus Z2. No, this should be, I messed up. It should be Z2 minus Z1. That is it. Looks a little messy, but if I think about it, I know what XA2 and XA1 are. They're numbers between 0 and 1. So this is some number. So that number is raised to the exponent, which is like Z, but it's like normalized Z. And that normalized Z, Z minus Z1 divided by Z2 minus Z1 is also between 0 and 1. Questions? Now, if I ask you about concentration of B, how would you get it from here?
We would find the concentration of A and then do 1 minus that.
So I know that XA plus XB is always 1, right? So my XB is 1 minus XA. So all of this is actually expressed in terms of XB. So if I take that at my point 1, XB1 is 1 minus XA1 and XB2. So that's just my boundary condition. XA2, right? So then this top is actually, let me change the color slightly. So this is my XB1 divided by XB is XB2. So it's actually more compact when I write it as XB. It's just that B is not diffusing, so I wasn't asking about it. A is diffusing, right? So again, remember that sum of x's has to be 1. Okay. All right. Well, that is our first problem in diffusion. Now we're going to basically, in the next couple of examples, what we're going to do is basically have more interesting cases, especially with reactions. And some of them are homogeneous, meaning that they're happening in entire medium. Some of them are heterogeneous, meaning that they could happen just on the surfaces. And that will kind of give me this different assumptions. So I will not be able to just say, oh, NB is equal to 0, because reaction will make that complicated, and I have to express it in some way in terms of NA. And that's essentially, from the mathematical standpoint, these boundary conditions, or what is happening inside of the medium, will change how I express NB instead of NA, and that will give me changed solution or different solutions to this problem. Okay. All right. I will see you on Friday. We're going to have one more homework. And basically, it's going to be assigned by Friday. It's going to be essentially diffusion problems. And that's going to be our last homework. It's going to be due the last day of class. Okay. All right. I see you on Friday.
Dr. Perdonovich, did you say anything about the exam at the beginning of class? I think I joined in a little late.
Yes, I just asked how was it. I did not grade it yet. So I will do that. I typically grade within 1 week of the exam.
Gotcha.
But did you have any comments? I was basically asking everybody what did they think of the exam, how did they feel about it. I didn't read your comments on the exam just yet.
Okay, well, I did have one comment that I wrote in there. I think I think I ran into this problem just because I don't know if you've seen my computer, but it's really, really big. It's like a 28.5 or 20. So when you like told us to have it like showing our work, it was really hard to read the problems on the screen because of the angle that I had to turn it down. It was like very, very weird for me.
I'll review. I don't think it's not. I mean, I reviewed a few videos. That's part of it. Like I have to kind of walk through them quickly. Yes, different people have different issues. It typically with the video and like your explanations, like it's pretty obvious that that's what's happening. So that shouldn't be a problem.
Oh no, I'm not like concerned that like you're thinking that I like did something weird. I was saying it felt uncomfortable, like the position.
Okay.
Like,
so next time we just have to. So what would you offer as a solution?
If we could like print out the exam or something like that, because like it's really hard to like do that thing where you like have the like actually look at the screen at the same time and then have the camera looking at your work.
Okay,
that's what I'm trying.
So for final, now technically I didn't announce that, but basically there was a folder at the same time of the exam. There was a folder called exam 2. Now those problems might not be visible anymore because they were timed, but there's like a folder that had basically those 4 images that I put in, so that can be printed. Now the only thing that I have to then make sure is that the whole thing allows you, but I did allow downloads, so that shouldn't be a problem at all, just the way it's set up already.
Yeah, I think
I just didn't expect people to go and print, because I didn't want to add that step.
Yeah, I understand.
But there would be actually, if you did it and we just know that like that can be done, that should be no problem at all to accommodate. Because as is, I'm allowing downloads because you have to scan the whole thing and email it to yourself, right? And when you email it to yourself, you got to be able to download, which is why I can allow the downloads. But then I can basically, the software allows me to see which web pages you looked at. and
Yeah.
at what time. It's the tracking is I'm actually in a shock. But
Oh yeah.
anyway,
Also, I had another issue too.
everything that
I
can
didn't-
be tracked, I know that it can be, but it's shocking to see it all in display. So anyway.
On the practice exam, or like the practice that we had, did you have the microphone setting on, or did you?
No.
Okay, so
I realized the video was recorded and not audio. And I figured audio is important if you end up talking on a phone or something like that. I should hear what's going on.
yeah, I had issues with that. So I tried to start the exam promptly at 7, but
Mhm.
it took maybe like I think somewhere from like 3 to 6 minutes, and then I texted the phone number you gave me, but then I realized it was a landline, or some the phone number you gave us, right? Is your landline.
No.
It was your mobile phone number.
Yeah. I don't
Okay.
have a landline. I don't
That's
own a
weird.
landline.
Okay, I'll send you what I got a message back, and I'll send you what happened. It said I had to like accept a thing to change it to voicemail. I'll send you the message. I'll
Okay,
show you.
maybe I was, because there was somebody else. So just to back, so somebody else had a problem. Try basically messaging in another way. This is this part of, so I was responding to my messages, but then I gotta do them in I actually had quite some traffic in responding to messages, but you don't know that I'm possibly already responding, and sometimes the things happen. So try to also email next time. What I did, I don't know whether that's a problem, but you did finish your thing on time. So
No, yeah,
I
I
don't
did.
think time was an issue. But in case it is, there was somebody else who had a technical problem. Also with the microphone, had to reboot the computer a couple of times. And I just I can manually extend your exam by 10 to 15 minutes for the
What's it
technical
called?
trouble.
Like for my computer, like for the camera, it will ask me like, hey, allow this for this website, right? It'll prompt up. The microphone, it doesn't do that for some reason. And so it just took I didn't do anything. It just like took a long time for it to say yes, like
Okay.
your microphone is on. I don't know why it didn't like automatically.
So
say,
again, I put the microphone in, and that I kind of added to the initial test, because I realized if I allow you to text me or call me, that's a good idea to have a track record of, because I'm allowing phone to be next to you, which is normally not something I allow during the exam.
Yeah.
So then if we can find a way, the main problem, like I found it a little unsettling, like it's so many things are solved when you can just be in the room with people, right? Then I can say, put your phones away, you have questions, I'm right here, right? And I can deal with
Also,
things
I had a
immediately.
question. On one, I was wait, did you do the answer key for the test yet or no?
No, I do that after I grade.
Oh, okay.
Yeah.
No, never mind then. I'll ask later.
Yeah, so I'll post and that partly because then I can respond also like, well, most of you did this, and this is what needs to be, and things like those, right?
Yeah. Okay.
So I need to grade to do that, to have that cumulative response. But yeah, but overall, I think you finished on time, so it seems that it was reasonable.
Yeah, I think it was. I got
How was
confused
the last
on
one?
Huh? The last
How
one
was
was.
the last one?
I thought the last one was easy. I thought the last one was easy. One was really hard.
It's just setting up. You don't have to solve it. You just set it up.
Yeah. Actually, so what happened with me is I think I started the last one and I had 20 minutes left. So I quickly, but I know my stuff pretty well. So last one was really easy, but one was hard. It just conceptually, like, I don't think we did a lot of it. And so I was very confused by the conduit.
I expected that one to be relatively easy, and that ended up being sort of, it's always counter what I expect somehow. I expected, actually, the way I actually set it up initially, I had first one is 15 points and the last one is 25. And then I decided, well, let me just make all of them equal.
I see.
And it would be interesting, like if I thought that it was the easiest one, and all of you, we'll see, I'll actually compare. Yeah, I think the only thing is like, because you have to make an assumption, but I think the first one is basically the indicative of what you always have to do with porous materials, because you always have to do approximations. Right?
Yeah.
And you will have various formulas at your assume that you're going into a new basin, and you have an exploratory well drilled, and then all of that exploratory well gives you formation evaluation, gives you like porosity log, right? And based on that porosity log, you want to investigate permeability. You also have to have geologists tell you something about the formations and their sands, sandstones, whatever it is that they are. And for all of those, you have these different correlations of how do you get permeability. Permeability is not easy to measure, but it's very important to know. So all of these exercises in transport actually gives us the foundation of how do I arrive at the correlations for permeability. Now, some of them I can sort of derive from analytical solutions, but there's all these simplifying assumptions you have to make to do that. Bundle of tubes is one of those, right? But bundle of tubes way will give you one way. If you did a proper network with interconnected tubes, that would give you another answer. Somebody could just like actually do some experimental measurements of permeability and plot them against porosity. That would give you a third, and you have to somehow reconcile. All of them are giving you a slightly different answer because all of them are approximations. And technically in porous media, what it ends up being is like, as long as you're on the same order of magnitude, you're happy, right? So that's the reality of porous materials. So, and I guess all of you were like kind of a little shocked by having to do that suddenly, right? In this course anyway. After focusing on analytical solutions, here we are, some correlations. Yeah.
Okay. Well, thank you.
Okay. I'll grade by Monday likely.
Okay. Thank you. Okay. Bye.
Bye.